Okay, the next topic in Chapter 4 is redox reactions. Now here's an example of one. Now we have some sodium metal. You can see the sodium metal over here. Nice silvery looking metal made up of sodium atoms. And then we have a bottle of chlorine gas. That's Cl2 gas. You can see the molecules of chlorine gas. Now when you put these two together, you add a little energy to it to get it going, it reacts pretty violently. Get a lot of heat produced. You see some vapor coming out of there. And we wind up with some sodium chloride. Sodium ions and chloride ions. Now here's the overall balanced equation. Now you can't tell by looking at this that this is an oxidation reaction. So let's take a closer look at it. First of all, I want to define the terms. Oxidation is the loss of electrons, and reduction is gaining electrons. Now you might be wondering, what's the point of the line over here? Well, one way that people used to remember the difference in the terms is to make up a mnemonic. And the mnemonic would be, Leo the lion says grr, meaning loss of electrons, oxidation, gain of electrons, reduction. In general, what we're going to see is that metals will lose valence electrons to nonmetals. And we talked about this back in Chapter 2 when we went into bonding. And when the metals do this, they wind up with a noble gas arrangement, and so do the nonmetals, for the most part. All right, so let's take a look at it in detail. So we start with the sodium atom. It's neutral, 11 protons, 11 electrons, and a neutral chlorine atom. And now we have our ions. And 10 electrons means sodium has the electron arrangement of neon, and chloride now has the electron arrangement of argon. So this is a very favorable reaction because both our products now are more stable than the reactants. And now what's going on with the sodium? Well, the sodium is losing the electrons, so it is said to be oxidized. The chlorine is gaining the electrons, so it's said to be reduced. Now there are two other terms with oxidation reduction, and that's oxidizing agent and reducing agent. The substance that is oxidized is called the reducing agent, and the one that is reduced is called the oxidizing agent. So agent means it's helping the other substance to do what it's supposed to do. So the reducing agent helps the other substance to be oxidized, and the oxidizing agent helps the substance to be reduced. I know it sounds kind of confusing, but just remember the terms are kind of opposites. Now we can write half reactions for these. A half reaction would be one separate for oxidation, one separate for reduction, and then we can add them together. So let's take a look at the first one. The sodium neutral atom is becoming a sodium ion and releasing the electron. That means the sodium is oxidized. It's the reducing agent. Now a second half reaction would show reduction. So the chlorine is gaining the electron, so therefore it is reduced and it's the oxidizing agent. We can add these two equations together and just bring everything down. And can we eliminate anything? Now we can eliminate the electron because that hasn't changed, but everything else is different. So that's then our overall equation for the reaction. Now let's take a look at another oxidation-reduction reaction. Here we're starting off with a piece of zinc metal, and this is supposed to represent the zinc metal here, and here's a bar of it. And when you put that zinc metal into a solution that contains copper ions, we can tell that because the solution is blue. There's a chemical reaction, and the zinc bar looks like it's turning black. It's turning dark anyway. Now what happens is, as it sits in the beaker, this is like the after beaker here. This is before and after. We get copper metal is being deposited right onto the piece of zinc. And now we have copper metal down here. So the zinc is being oxidized. It's losing electrons. See how the zinc ions are down here now. And the copper ions are being reduced. Now you should have done this type of thing in one of the labs that you had when you started with some copper 2 nitrate, and at the very end you added aluminum metal to get the copper back again. Well, that's another example of oxidation reduction. The zinc, because it was oxidized, is the reducing agent, and the copper ions would be the oxidizing agent. And here's another example. This is a real interesting one. Maybe you can get your lab instructor to do this one. If you take a piece of copper metal, it can be a penny, or it can even be a piece of copper wire, which actually works better. You can take that copper wire, and again we're starting, this is the before picture. You can put a piece of copper wire in a solution that contains some silver nitrate. Now silver nitrate dissociates into silver and nitrate ions. The nitrate is just going to be a spectator. So what happens over time is, let me get my arrow here, is the after. What happens over time is that the copper metal becomes copper ions, and we can see that the blue color is appearing. And then you get little crystals of silver forming all over the copper ions. Looks pretty cool. It can go pretty big. That's pure silver now. So here's the overall equation up here. We see that the copper is losing electrons, it's being oxidized, and oops, let me go back here. And the silver is being reduced, the silver ions. Now you're going to be asked what's being oxidized and what's being reduced, and also to find the oxidizing and reducing agents. So we're going to spend some time in this lecture going through that. So the next question here, we see that at the bottom of the slide, is how do I assign oxidation numbers to particles in a reaction? All right, so there are rules we're going to follow for that. Now this is table 4.2 out of the text. And so we'll go through these slowly. Let's start at the top. So we have an atom that's all by itself, and an element is said to have no charge, is overall neutral. We saw that with the metals in some of the examples. If you have a monatomic ion, the charge of the monatomic ion, where my arrow went to, here it is, the charge of the monatomic ion is its oxidation number. So the oxidation number of the sodium ion is +1. The oxidation number of the chloride ion is -1. Now fluorine is given its own special rule because fluorine, when it's in a compound, will always be -1. And we can use that to figure out, here we go, we can use that to figure out what the charge is of the other element that's with the fluorine. So we're going to be doing that in a moment. Oxygen will almost always be -2, but here's an exception when it's in peroxides. Then it's only -1. Hydrogen will almost always be +1, but there are exceptions for that too. But mostly we're just going to see the +1. Right, so let's try 3 of them. So we have lithium oxide, nitric acid, and the dichromate ion. And we're asked to find oxidation numbers of all 3. So I'm going to go through each one of these one at a time. So the first one we're going to take a look at is the lithium oxide. Now lithium on an ion can only have a charge of +1. And oxide has a charge of -2. Remember this from you should remember this from chapter 2 when we wrote formulas for compounds. And so therefore the oxidation numbers are looking right back at you, +1 and -2. For the other two particles, it's going to be a little bit more involved. So let's take a look at the nitric acid. HNO3. Now the question really is, what's the oxidation number of the nitrogen? In order to figure that out, we have to know what the oxidation numbers are for hydrogen and oxygen. So remember from the rules, hydrogen will have an oxidation number of +1. Oxygen will have an oxidation number of -2. So let's take the compound apart. So we have +1 for the hydrogen, and because we have 3 oxygens, that's going to be 3 times -2, or -6. So therefore, what does the nitrogen have to be if the overall charge adds up to 0? And the reason I know it adds up to 0 is there's nothing written in the upper right-hand corner. See up here? There's nothing written in the upper right-hand corner, which means the charges add up to 0. So what does the nitrogen have to be? It has to be +5. It's pretty straightforward, pretty easy to do. Now, what if we have an ion that doesn't, where the charges don't add up to 0? That's going to be the same thing. Well, the only difference will be the total charge will have to be -2. So let me get my arrow back here again. Here we go. So we have 2 chromiums. That's the one we're really trying to find out. So I'm going to put an X in for the charge of each chromium. So there's 2X then. 7 oxygens is going to be 7 times -2. And then the total overall charge is adding up to -2. And the question is just then, what is the value of X? So to work that out, multiply the 7 times -2, we get -14. Now we want to get rid of the minus 14, so we're going to add 14 to each side, which will give us 2x equals positive 12. And then we're going to divide each side by 2, so we get x equals positive 6. So then each chromium atom in the dichromate ion has an oxidation number of positive 6. They're not going to become any more complicated than this. Now here are some for you to try. So you want to pause the screen and come up with the oxidation numbers of the underlying elements. And after you've come up with your own answers, then we'll go through the solutions to it. Okay, now here are the solutions. Sulfur, 2 oxygens, so the sulfur has to be positive 4. The carbon in the carbonate ion, notice that the charges are adding up to minus 2. The carbon has to be positive 4. And then we have the sulfur down here in sodium sulfate. Now sodium can only be positive 1. There's 2 of those. And we just kind of work it out. What's the sulfur going to be? And finally, we get sulfur being positive 6. And then we have what's the nitrogen in the ammonium ion. Same thing, N plus 4 times plus 1 equals plus 1. And we're going to wind up with N being minus 3. Now we can go over later why we have these charges. Where do they come from? Can it be any old charge at all? And the answer is no for that. But we will be going over how we could figure out what these charges are using our ideas of atomic structure. Okay, so how do you recognize a substance has been oxidized? Well, the charge has to go up. So what we have to do is locate a substance before and after the reaction and see what's happening to its charge. So here are some examples of the charge going up. For the sodium, it's 0 to plus 1. For the iron, plus 2 to plus 3. And for the nitrogen, minus 3 to 0. So in each of these cases, the charge is going up. So if the charge goes up, that means that the particle is being oxidized. And one thing I want to note here, we're always talking about the reactants, never the products, just the reactants. All right, so let's try to do this in this reaction. So we want to know what's being oxidized and what's being reduced. So what we'd have to do then is write the oxidation numbers for all the particles that we see in our equation. So we're going to assign oxidation numbers to everything. So if you're not sure how to do that, you want to go back and look at the rules. So here we go here. Here's my equation again. So I have 2 chlorine atoms. Each of those will be 0. I have 2 potassiums. Each of those will be plus 1. 2 bromides. Each is minus 1. Then on the right-hand side of the equation, I have 2 bromines that are 0, and 2 potassiums plus 1, 2 chlorides minus 1. So the chlorine is changing oxidation number, and so is the bromide. Notice the potassium isn't doing anything, so we kind of forget the potassium then because it isn't reacting. So the chlorine atom then, because the charge went down, 0 to minus 1, it's being reduced. And the bromide ion, because its charge went up, is being oxidized. Now here's another reaction that we've seen before. And you see, in fact, you see this all the time, burning the methane gas in the laboratory, the Bunsen burner. And so is this an example of oxidation? Well, oxidation at one time used to mean reacting with oxygen, so I guess this is. But let's take a look at it in terms of electrons. So the first thing we want to do is come up with the oxidation numbers of our reactants and products. In CH4, since each hydrogen is plus 1, the carbon must be minus 4. Now we know we have O2, they're going to be neutral. So that's 4 oxygen atoms with no charge. Now on the right-hand side we have CO2. The carbon must be plus 4 because it's with 2 oxides. And in the water we have 4 hydrogens plus 1, and we have oxygen, or oxide, is minus 2. So we can see then what's changed the oxidation number? Well, definitely the carbon, minus 4 to plus 4. And the oxygens have changed. Notice that the hydrogen hasn't changed anything. So the carbon then is being oxidized, and it's losing 8 electrons. That's a lot of electrons. And the 4 oxygens are gaining those 8 electrons. Each oxygen gaining 2. One thing you want to note that the number of electrons lost and gained are always equal in these reactions. So here's some for you to try now. Assign oxidation numbers and determine what is being oxidized and reduced. Identify the oxidizing agent and the reducing agent. So you want to copy these down on a piece of paper and try them, and then you can come back and look at the solutions. Okay, so I'm going to go through these one at a time. Alright, starting with the first one. Assigning oxidation numbers, we would get the aluminums as neutral. Iron is +3, oxide is -2. Aluminum is +3, again oxide -2, and the iron is neutral. So you can see that the oxide hasn't changed. So the aluminum has changed, it's lost 3 electrons for each aluminum, and because we have 2 aluminums there, that's a total of 6 electrons being lost. So aluminum then is the reducing agent because it's being oxidized. And then we have the iron, which is the opposite now. The iron's going from +3 to 0, and there are 2 of them. So that's gaining 6 electrons. And that's reduction. So the iron 3 oxide is the reducing agent. One thing you want to note here is even though the oxide didn't do anything, when I ask you what's the oxidizing or reducing agent, it's the whole compound that's given as the answer, not just a particular part of the compound that's actually reacting. Okay, the next one we have, again, sulfur dioxide reacting with oxygen, giving us sulfur trioxide. Okay, taking everything apart. Here are our oxidation numbers. So each oxygen is -2. There are 4 of those altogether. And we have 2 sulfurs. So for the total charge to be 0, the sulfur must be +4. And we have 2 oxygens, 0. And you notice now on the right-hand side, we have oxygen. It's see, some of them are on the right-hand side. They're all -2, but you notice on the left-hand side we have oxygen is -2, and we also have oxygen at 0. So it's these oxygens that are actually changing oxidation number, not these 4, but just 2 of those. All right. So the 2 sulfur atoms were +4, and now they're +6. So then each sulfur must be losing 2 electrons for a total of 4. So the SO2 is the reducing agent. The 2 oxygens that were neutral, each of them are gaining 2 electrons. So a total of 4 electrons. So therefore, that's reduction, and that means that is the oxidizing agent. Again, you notice that the number of electrons lost and gained are equal. So here we have the last one. Now, if we write down all the oxidation numbers, we get fluorine's neutral, calcium +2, chloride -1. On the right-hand side, calcium +2, fluoride -1, and the 2 chlorides are neutral. So the calcium then hasn't done anything. So it's the fluorine and chloride. So the fluorine atoms are gaining 2 electrons. That means they're being reduced. Therefore, it's the oxidizing agent. And the 2 chloride ions are losing 2 electrons. That means they're being oxidized. It's the reducing agent. Now, there's going to be an assignment on Connect for you to do where you have to do the same kind of thing. And these questions, again, are right out of the text. And that's the end of the show.